Welcome to the Agrawal classes. I am Ajit Agrawal and we are studying thermodynamics for BE first year students. Today we will discuss the Carnot cycle. In this Carnot cycle, we are having the four processes and all the processes are reversible process. The process 1 to 2 is constant temperature process, and say at this particular point the temperature is TH. So 1 to 2 is constant temperature process, 2 to 3 is adiabatic process, where PV to the power gamma equals to constant, and 3 to 4 is again constant temperature process or the isothermal process, and at this point the temperature is say Tc, and process 4 to 1 is adiabatic process, adiabatic reversible process, where PV to the power gamma equals to constant. So on the PV diagram we are observing this and how this Carnot cycle works. In this Carnot cycle, here we are having this piston and cylinder and this piston arrangement. So at this particular point here we are having a gas, that is our system where we are focusing our attention. So let us start with the process 1 to 2. It is an isothermal expansion. So in this particular time what we will do, we will put here a dithermic wall on the top of the cylinder, and it will be connected with the source T1. So the heat will be transferred from the source to the gas and the piston will move backward. So this is the expansion process 1 to 2 going on, and this process is very slow because when we say the reversible, there should not be any temperature difference between the source and the gas. So this process will take place gradually and the piston will move backward. When we reach to the point 2, say up to this point somewhere we have reached, so at this particular point, say 2 point, we'll remove this dithermic wall which is conductive, which transfers the heat, which allows the heat to enter. We'll remove this dithermic wall and instead of this we'll put the adiabatic cover, say the B name, adiabatic cover at this place, and then the piston will move further backward, that is the expansion will be happening as PV to the power gamma equals to constants. As we are putting this adiabatic wall here, so there will not be any heat transfer from this head, and already the cylindrical surface is adiabatic. So for the process 2 to 3, the expansion will be adiabatic reversible process where no heat transfer will take place, only the work or the expansion work will be there. When we will reach to the point 3, at point 3 we will again start moving backward as a constant temperature process. So say from this point to this point again we are coming backward. At this time we will remove this adiabatic wall and instead of that we will put the dithermic wall here, and this dithermic wall will be connected with the sink T2, the sink whose temperature is T2 or TL, as we said, lower temperature. So when this piston will move forward towards the left side, the gas will reject the heat at constant temperature, because we don't want that there should be a temperature gradient. If there is a temperature gradient, then this process will not be reversible. So this piston will move very slowly so that there should not be a temperature gradient, and the heat will be transferred from the cylindrical system to this sink up to point 4. So 3 to 4 is isothermal compression, and from 4 to 1, at this point we will remove this dithermic wall and we will put again the adiabatic wall here, and then the piston will move very rapidly so that there should not be heat transfer going out or the heat going out of this, and that is the compression. So 4 to 1 is the adiabatic compression. So we'll complete the cycle. So in this Carnot cycle we are having the 2 isothermal process and 2 reversible adiabatic process. So let us find out the work done in each process. So process 1 to 2, as I said, it is isothermal process. So in isothermal process the work done is given as W12 and it is an isothermal process. So from the first law of thermodynamics, Q minus W equals to du, and du is 0 because temperature is constant. So du is 0. So Q minus W is 0. That is W12 is equals to Q12. That is heat supplied during the isothermal expansion process. And work done is given as P1 V1 log of V2 upon V1. So here P1 we are saying, T1 we are saying as the TH. At point 1 it is TH and at point 2 it is TH. So the P1 V1 can be written down as MRTH log of V2 upon V1. So this is the work done during the process 1 to 2 and it is equals to the heat transfer during the process 1 to 2. Now let us consider the process 2-3. The 2-3 process is reversible adiabatic process where PV to the power gamma is constant and the temperature at point 2 is TH and at point 3 the temperature is TC. So the expansion is taking place from TH to TC. The temperature drop and the pressure drop is from P2 to V3, volume increase from V2 to V3. So in this particular case, the work done for the process 2-3 is given as P2V2 minus P3V3 upon gamma minus 1. So this can be written down as Mr gamma minus 1 TH minus TC. As we know that R upon gamma minus 1 is CV, so this can be substituted as MCV TH minus TC, where TH is the temperature at 2 point and 3 TC is the temperature at point 3. So this is the work done during the process 2 to 3. Now let us find out the work done during the process 3-4. This process is reversible isothermal process and this process is taking place at temperature TL or TC, lower temperature, or you can say cooler temperature. TC is equals to constant. So we are saying here as TC. So that work is given as W34 is equals to Q34. Again the same, change in internal energy is 0 because it is isothermal process. So Q is equals to W. So W34 is equals to Q34 is equals to P3V3 log of V4 upon V3, and this P3V3 can be written as MRTC log of V4 upon V3. So that is the work done and the heat transfer during the process 3-4. They are equal. Process 4 to 1 is the reversible adiabatic process. Process 4 to 1 is reversible adiabatic process where PV to the power gamma equals to constant, and this process is a compression process. Here the pressure is increasing and volume is reducing. So in this particular case, the temperature at point 4 is TC, cooler temperature or lower temperature, and at point 1 it is temperature, higher temperature or hotter temperature. So work done is given as P4V4 minus P1V1 upon gamma minus 1 is equals to Mr gamma minus 1 into TC minus TH. That can be written down as MCV TC minus TH. So that is the fourth work done. So now if we want to find out the area under this curve, that is the work done during the cycle, then we will sum up all these work. So net work done during the cycle 1, 2, 3, 4, 1 is the equation 1 plus equation 2 plus equation 3 plus equation 4. So that is the total work done. Here if you will see MCV TH minus TC and MCV TC minus TH, so this will cancel out. So you will be left with the first and the third term, MRTH log of V2 upon V1. Here we are writing minus, as here it is V4 upon V3, so we are reversing it V3 upon V4, so it becomes minus RTC log of V3 upon V4. Now this is the work done. Let us find out the heat supplied. So heat supplied during this process, this cycle is only between the 1 to 2 process, that is the heat supplied. During the process 3 to 4, it is the heat rejection. It is not the supplied, it is the heat rejection. So during this cycle, whatever the heat we had supplied is 1 to 2 only, and that is given as the process 1 to 2, work done is equals to heat supplied, so it is equals to mRTH log of V2 upon V1. So we know the heat supplied during the cycle. Now to find out the efficiency of this cycle, the formula is work done upon heat supplied. So work done, net work done we had calculated as mRTH log of V2 upon V1 minus mRTC log of V3 upon V4 divided by heat supplied, this one mRTH4 log of V2 upon V1. So if you will calculate this, it becomes the MR will cancel out, TH minus TC upon TH. This V2 upon V1 and V3 upon V4 are equal. V2 upon V1 is equal to V3 upon V4. This log of V2 upon V1 and log of V3 upon V1 and log of V2 upon V1 are same, so they are cancelled out. So the efficiency is given as TH minus TC upon TH. TH is the higher temperature and TC is the lower temperature. So T1 minus T2 upon T1, that is heat work done, we can also write down as the heat supplied minus heat rejected will be the work done. So Q1 minus Q2 upon Q1. So it becomes 1 minus T2 upon T1 is equals to 1 minus Q2 upon Q1. So this is the efficiency of the Carnot cycle. If you wish to represent this Carnot cycle, then how we are representing it? We are writing this as a higher temperature reservoir. From this we are having an heat engine, a reversible heat engine. In this case it is a Carnot cycle. When we say the Carnot cycle, it is a reversible cycle because all the processes are reversible, and here it is rejecting the heat to a lower temperature sink T2. So it is rejecting Q2 amount of heat, it is taking Q1 amount of heat and is producing work equals to Q1 minus Q2. So the efficiency is given as Q1 upon Q2 output divided by heat supply Q1. Or if you write in terms of temperature, then it becomes the T1 minus T2 upon T1. So this way we have the Carnot cycle. The Carnot cycle basically gives you the maximum possible efficiency between these two temperatures. If the temperature T1 increases, then what will happen to the efficiency? You can see from this equation 1 minus T2 upon T1. If T1 is increasing, then this T2 by T1 will reduce. That is, the efficiency will increase. That is, if you are increasing the source temperature T1, then the efficiency increases. If you reduce the temperature T2 to lower side, then in this case again T2 by T1 will reduce. So if you are reducing the T2, the efficiency is increasing. So whenever we want in general to find out that if the inlet temperature or the heat supply temperature is higher and higher and higher, you can expect more and more and more efficiency. If the rejection temperature is lower, then you can expect again the more and more and more efficiency because you are working in a wider range. So that is the Carnot cycle. Let us consider why this Carnot cycle is impractical. There are number of reasons. First, it demands the process should be reversible. So for the reversible process, there should not be any friction between the piston and the cylinder, which is not possible. So the process cannot be reversible. Isothermal heat addition is not possible because the heat transfer takes place only when there is a temperature change. Although we can reduce the temperature difference, but if we are keeping this temperature difference, then this process is not a reversible process, and as we go on reducing the temperature difference, the heat transfer takes longer time. And the third one is the isothermal process is a very slow process, and the reversible adiabatic process is very fast process. So this type of movement is not possible in the piston cylinder arrangement, that up to a certain stage the piston moves very slowly and then suddenly it starts moving at a higher speed, and then again it starts moving at a slower speed, and then again it starts at a very fast speed. So this type of mechanism is not possible. So the isothermal process which needs very slow movement and adiabatic process which needs very fast movement of the piston is not possible. And finally the change of dithermic and adiabatic cover is not possible when the piston cylinder arrangement is running at a higher speed. So that way there are number of reasons why we cannot go for the Carnot cycle, or it is impractical cycle. Although one more reason is there, even if it is possible, then we are not going to use it, because when you will consider the PV diagram of the Carnot cycle, the work done during each cycle is very less. We get more work during the expansion process, but most of the work from this expansion process is consumed during the compression process. So what we left is very less amount of the work during the cycle. That is, the area under the PV diagram of the Carnot cycle is very less. So that way also this is not feasible. So these are the limitations, these are the reasons why the Carnot cycle is impractical. Now let us consider the Carnot theorem. The Carnot theorem states that all the engines operating between a given source and a sink, none has higher efficiency than a reversible engine. That is, if the engines are operating between two temperature sources, the T1 the source and T2 the sink, and here the number of engines are operating, then the efficiency of the reversible engine will be higher than the efficiency of the irreversible engine. So that is that all the engines operating between a given source and sink, none has a higher efficiency than a reversible engine. That means the efficiency of reversible engine will be higher than the efficiency of an irreversible engine if both the engines are operating between the same source and same sink temperatures. So we will have to prove that whether the efficiency of the reversible engine is more than the efficiency of the irreversible engine operating between the same temperature limits. So here let us consider I be an irreversible engine and R be a reversible engine, and let us assume the opposite of what we want to prove. Here we want to prove that the efficiency of the reversible engine is more, so let us assume that the efficiency of the irreversible engine is more than the efficiency of the reversible engine operating between the same temperature limits T1 and T2. So the efficiency is given as output upon heat supplied. So we are keeping the heat supplied constant. So Wi upon Q1, that is the efficiency of the irreversible engine, will be more than the efficiency of the reversible engine Wr upon Q1, as we had assumed. So that means the work output from the irreversible engine will be more than the work output from the reversible engine for the same amount of heat supplied. So here let us consider how they are operating. Here we are having the two temperature source and sink, and here the reversible engine is there, which is taking Q1 amount of heat from the source and converting it into a work as Wr and rejecting the Q2 amount of heat to the sink at temperature T2. And the irreversible engine is also taking Q1 amount of heat from the source at temperature T1 and converting it into a work as Wi and rejecting Q2 dash upon of heat to a lower temperature sink at temperature T2. So as we said, Wi is more than Wr, so the heat rejected Q2 dash will be less than Q2. Because the Q is same, Wi is more, so Q2 dash will be lower than Q2. So that is the given thing. Now if we'll combine these two units together as one unit, so what we can do, we can have this, as it is a reversible engine, we can operate this in the reverse direction also. Then only we said it is a reversible process. At any stage you can stop the process and you can reverse, and you can go to the original position with the system and the surrounding. So if we will reverse this heat engine, we will operate in the reverse direction. Then to operate in the reverse direction, instead of getting work, we have to supply the work. Instead of rejecting the heat at Q2, we will take the heat of Q2 and we will supply it to a higher temperature as Q1. So it becomes the heat pump. When the heat engine is operating in the reverse direction, it becomes the heat pump. So here it is the heat pump. It is taking Q2 amount of heat from the lower temperature reservoir and getting the WR work, as it was putting the WR work output. So here it is consuming the WR work, and then it is rejecting this total heat Q2 plus WR as Q1 to a higher temperature source. That is, in this case, it is the sink at T1 temperature. To get this WR, what we will do from this irreversible engine, as WI is more than WR, so from WI we will take that WR to run this heat pump, and the remaining amount of work we will get as an output. WI minus WR we will get as output. So this is the combined unit. If you see this figure, here the Q1 amount of heat is supplied to the sink source T1 at higher temperature, and here it is taking the Q1 amount of heat as the irreversible engine from this temperature source C1. That means this temperature source is not required. We can directly connect this. So here I am connecting it directly, that it is directly connected. The heat pump is rejecting the heat and that is supplied to this irreversible engine. And this irreversible engine is rejecting Q2 dash amount of heat, which is lower than Q2. So here heat entering is low and heat going out is higher in this particular combined system. That means the net amount of heat going out of this sink is Q2 minus Q2 dash, and you are getting the work output as WI minus WR without connecting with the other sink or the other reservoir. That means here you can say, if you can reduce this also as one unit, so you are having a reservoir at temperature T2 and is taking the heat. This combined unit is taking the heat Q2 minus Q2 dash from this reservoir and converting it into a work. This is not possible from the fundamental law, the second law of thermodynamics, that entire heat cannot be converted into work. That means what we had assumed is wrong. The maximum it will be a 0. That means the efficiency of the irreversible engine is equal to the efficiency of reversible engine. But as when it becomes 0, this irreversible engine will also become the reversible. Otherwise, the efficiency of the irreversible engine is lower than compared with the efficiency of the reversible engine. That is the Carnot theorem, and we can prove by this way. Let us discuss about the corollaries of the Carnot theorem. The efficiency of all reversible heat engines operating between the same temperature limit is the same. So whenever we are having the reversible engines and they are operating between the same temperature limit, then the efficiency of all the engines will be same. We can conclude one more thing, that the efficiency of the engine is independent of the nature or amount of the working substance undergoing the cycle. Because in this particular case, we are having only the temperature as the criteria, the maximum temperature and the minimum temperature. If they are the same, then the efficiency of the reversible heat engine is same. So it is independent upon the nature and amount of the working substance undergoing the cycle. Let us consider the corollaries of the second law of thermodynamics. It states that there are number of corollaries. The first, it says that no heat engine working in a cycle between two constant temperatures can be more efficient than a reversible engine working between the same two reservoirs. That is, the efficiency of the heat engine, real heat engine, is not greater than the reversible engine operating between the same temperature limits. All reversible engines working between the two constant temperature reservoirs have the same efficiency. Then the third one is a temperature scale which is independent of thermometric substance or working fluid is called as thermodynamic temperature scale. The fourth corollary is it is impossible to attain a negative temperature on an absolute temperature scale, that is Kelvin. And fifth one is, for cyclic process, the cyclic integration of quantity del Q by T is always less than or equals to 0. That is, cyclic integral of dq by t is always less than or equal to 0. This is known as the Clausius inequality. And the last corollary is there exists a property of system called as the entropy, which remains constant for all reversible processes and increases for all real processes. So there is a property called entropy which remains constant for all reversible processes and increases for the real processes. So this is all about the Carnot cycle, the Carnot theorem, the corollaries of the second law of thermodynamics, corollaries of the Carnot theorem we had discussed. In the next class, we will consider the Clausius theorem and Clausius inequality, and then we will derive the property, the entropy. And of deriving after the entropy, then we will come to the principle of entropy increase. In the next class, we will consider all this. Thank you.